think we are on business. So welcome to today's HJAC. Today's speaker is Yamila Miguel, who is an associate professor in Leiden Observatory and also senior scientist in ESTRON, which is the research institute in space of the Netherlands. Yamila earned her PhD in 2011 in Universidad Nacional de La Plata in Argentina and was supported by CONICET, which is the National Research Council in Argentina. After that, she was a postdoc in Max Planck Institute for Astronomy here in Heidelberg in MPIA. And later on, she was a fellow, a Kennes Fellow and Poincaré Fellow in Observatoire de la Côte d'Azur in Nice in France. In 2018, she was appointed professor in Leiden Observatory, and she also earned a ERC Consolidator grant in 2023. The title of her talk today is Peering Inside the Giants, How Solar System Information and JWST Data Transforms Our Understanding of Exoplanet Interiors. The floor is yours.
So before starting with the talking about the giant planets, I wanted to tell you a bit more about what we do in my group. So here is a picture of everyone in the group with a few guests. So this guy here is not in my group. He's actually here, but was visiting us. And this is Prune, also was visiting. But the rest is my team. And what we are doing is to try to understand and characterize planets, solar system planets, and also exoplanets. Not only giants, although giants will be the topic of the talk today, but we also work with the smaller planets. And I'm interested to talk more about it if you want later on. Now, going into the topic of the talk today, I first wanted to start saying which are really the main questions in the field. And what we would like to know regarding giant planets is first, how is that planets work? This is a very basic question, but we still don't know about this for giant planets. We don't know if they are fully convective in their interiors, if they have radiative zones, if they have some regions where the material is not homogeneously distributed. We don't know about their cores. The interactions between interiors and atmospheres. There are really lots of questions that we still don't know about the basic functioning of giant planets. And this is really one of the things that I want to know. I want to know more about how is that planets work and what we can learn also from the observations about this. The other big question in the field is related on how is that planets form and evolve. We don't know. There are different theories that explain the formation of giant planets. And we still don't know which one of those is the right one. Even inside one of the theories, there are different flavors. So this is really a highly debated topic. And one of the ways, of course, of learning about planet formation and evolution is understanding the planets themselves. So that is why these two questions are actually related. And the other one is, of course, about the evolution, especially if we think of the observations that we are doing today. We are observing the planets in one specific time, but of course they evolve with time. And it's not that they are always the same as we would like to think for giant planets, but that is not true. So specifically during the talk, I will be first talking about planetary interiors, about the amount of metals that we have in the interiors and how these metals are distributed. And I will tell you which are the lessons that we learn from solar system and that we are trying to apply to exoplanets. And during the second part of the talk, I will focus more on the atmospheric part of it and specifically try to see how is that these metals that the planet has evolved with time. Just to make sure that we are all on the same page when I say metals and metallicity, and I will.
So in our solar system, Jupiter and Saturn were the first planets that were born. This is because they are born from the disk of gas and dust that forms around the star after the star is formed. And we need to have that gas in order to form the giant planets. And the gas dissipates in a few millions of years. So actually, the gas giants, even though they are so big, they form much faster than the smaller planets that take longer time scales. And because of that, they have very valuable information in their interiors and atmospheres to understand those first stages of the planet formation process. So this is one of the reasons why it's important to understand more about their interiors and their atmospheres, but it's not the only one. Another reason is that because they are so massive, they are really the ones that dominate the dynamics of the entire planetary system. In the case of our solar system, again, Jupiter and Saturn that were born very early on, they were moving around during their formation and evolution, and that really was steering the orbits of all the other smaller bodies. So they have a huge influence on how the planetary system is going to end up. That's why I put the architecture. And even they might have some implications for potential habitability of planets, delivery of water, and other things happening also to smaller planets as well. So that's why we want to understand how is that these planets were born and where is that they were born. And this is actually an open question, even for our solar system. We still don't know where is that Jupiter and Saturn were born in the first place. Third question, third reason of why, these are my reasons, by the way. Maybe you also have other reasons, right? Why we care about these planets. But these are mine, and I think that one that I really care about is that giant planets are natural laboratories, in the sense that in the interiors of these planets, we have conditions that we don't have in other bodies. For example, in the interior, in the very center of Jupiter, we have 20,000 degrees and 1,000,000 bars of pressure. And those conditions, we don't find them in the stars, we don't find them in other objects. So they also push us to try to understand the basic physics of things like how hydrogen behaves, how helium behaves, what happens when you have mixtures. Is it possible to have rocks that are solid at that state, or are they liquid, or what happens with ices? So all of those questions that we turn out doing lab experiments and calculations, all of those are motivated because we want to understand the interiors of these planets. And that's why I say that they are natural laboratories. It's not that we really probe the interiors, but they are our excuse and motivation to study those fundamental physics. Number 4 is that they are easier to characterize with current technology. So we have huge telescopes from the ground, telescopes on space, and the bigger the planet and the closer to the star, the easier it is to characterize them. So this is also why this is a good moment to study giant planets. And the final one is that we got great data with missions in our solar system. We recently went to both our giants, to Jupiter and Saturn. Saturn with the Cassini mission that was orbiting Saturn for more than 20 years and gave us amazing information to understand that planet. And more recently, we had the Juno mission that has been orbiting Jupiter since 2016, and it's still there. And those missions really changed our views on the interiors of the planets. So I will tell you a little bit more about that. This movie that you are seeing is from the Juno mission. This is Jupiter, and you are seeing a succession of time lapses when the spacecraft is passing by very close to Jupiter in one of the orbits. Right now, we have more than 80 orbits already. And all of that is really giving us a lot of great information to understand this planet. So here you can see that the orbit also passes through the poles. So here we have an image of the pole of Jupiter that we never had before because of the other spacecraft like the Voyagers. They didn't pass through the poles, they passed through the equator. So this specific orbit that the Juno mission has allow us to get better information on the gravity. And this is really what I use to make the interior model calculations. How is that we use this information? So imagine that you have Jupiter here, and Jupiter would be a perfect sphere with the mass equally distributed. If that is the case, then we can calculate with simple celestial mechanics, which would be the orbit of the spacecraft. Now, in reality, what happens is that the spacecraft deviates from the perfect orbit, and those deviations from the perfect orbit are because the planet is not a perfect sphere with the material equally distributed. So then by studying this, we get a map of the gravity field around Jupiter, and this is what I use in the interior models. I try to see which is the density structure in the interior of the planet that will match the gravity field that we obtain with the spacecraft. So we have this very accurately measured for Jupiter. And for Saturn, it's also quite good. It's not the same level as Jupiter, but it's still very good. For Uranus and Neptune, it's not so good because we only have one passage of the Voyager 2 spacecraft, and that's the only data that we have. So if you compare the error bars of the information that we have for Jupiter and Saturn is tiny, tiny, and for Uranus and Neptune is huge. So definitely it would be nice to get more info on those ones. All right, but what is it that we learned with this information? And here, what I'm showing is really the state of the art today of how is the interior structure of Jupiter, or what we believe is the interior structure of Jupiter. And this is just a schematic view. So let me walk you through this. Here, what you see is that Jupiter has an external layer that is dominated by molecular hydrogen and helium. Then when we go deeper down, you see these droplets, these yellow droplets, is because there are two things happening there. One is that hydrogen has a phase transition. It changes from being behaving like a molecular gas to being a metallic fluid. So it behaves like a metal, like a metal. This transition only happens in the interiors of the giant planets. It doesn't happen in the stars, for example. So it was quite unknown for a long, long, long time. We only got confirmation, experimental confirmation of this phase transition a few years ago. So this is something that we kind of knew from models, but we didn't have confirmation until I think 10 years ago or something like that. The other thing that happens here is that hydrogen and helium also have some kind of phase transition. So in the atmosphere, hydrogen and helium both are, they are very well mixed together, right? They have no problems with each other. But when we reach these temperatures and pressures at this point, then there is an immiscibility region. So they separate. They just don't want to be together anymore, like water and oil, and they separate from each other. And that's why we have this separation here in between two layers. This happens in the interior of Jupiter and also in the interior of Saturn. We have no idea if this might happen in exoplanets. And the thing is that we also have only experimental confirmation a few years ago of this, even more recently than the other one, actually. I think the publication is 4 or 5 years ago. And there is only one paper. So there is still a lot to learn about this immiscibility in the interior of Jupiter. When we go even deeper down into the planet, because helium forms droplets here, these droplets are heavy and then they rain down. So then we have an overabundance of helium in this part and a depletion in the atmosphere that we actually observe. So we observe this depletion in helium in the atmosphere of Jupiter, and that's why we knew about this immiscibility even before we observed that in lab experiments. And of course, we also have metals here, but hydrogen and helium are the vast majority of the material. When we go even deeper down, let's go to the very center of the planet. Here we have a core made of 100% metals. And what we thought before the Juno mission was that this core was actually quite large. The estimations were of around 15 Earth masses. And that was a very sharp transition between the core and the envelope. But with the Juno data, we actually realized that this needs to be diffused. So there is this other layer that we call the dilute or diffuse core, where the 100% metals in the core are mixed with the hydrogen and helium envelope. And this is the only way that we can explain really the gravity data. And this was also backed up by experiments that were done with rocks and ices and the mixtures of those with hydrogen that we know that is possible. So this is really our picture today. The actual core of 100% metals is quite small. We think that maximum is probably something like 7 Earth masses and maybe even smaller if there is a core at all. It might be that everything is diffused in the envelope. That's also a possibility. If we look at Saturn, you will see that it looks more or less the same. But this information, we actually got it in a different way than Jupiter. Because for Saturn, what we have is that the planet oscillates, similar as stars oscillate, but different mechanisms. We believe that Jupiter also oscillates, by the way, but we never measured those oscillations. But in Saturn, because we have the rings, these waves propagate to the rings, and we can do ring seismology. And that is the way that we actually could probe the interior structure of Saturn. And we know quite well the structure, and we know that this region here is similar to Jupiter. So we also have these dilute core structures for the case of Saturn. So it's interesting to see that both our giants have these kind of structures where the interior of the planet is not fully convective and fully mixed, as was really our view only a few years ago. So this is something that really changed in the last year. And these inhomogeneous structures were also found recently with planet formation models. So when you try to form the planet, giant planets, especially those calculations were using the core accretion, where you start with the solids first and then you start accreting the gas, they naturally form those inhomogeneous structures as well. So we believe that this structure that we observe in Jupiter is actually there from the formation of the planet itself, and that it changed slightly during the evolution, but it still is, let's say, a fossil from the formation of the planet. All right. Now, I want to motivate a little bit all the information that we have from the solar system, but also what we learn from exoplanets, because I think that it's very important to put all this information together if we want to move to the next step, understanding the internal structure of planets. And from exoplanets, we have more than 5,000 exoplanets discovered. And we also have great information on their atmospheres these days. And one of the reasons why we are getting such great information on their atmospheres is JWST, that space telescope that we had there since 2 years ago. And the way, or one of the ways that we use JWST to observe atmospheres of planets is that when the light of the star is passing through the atmosphere of the planet, we actually see the planet in different sizes depending on the wavelength. So this is like what we call a transmission spectrum. And we use this. Of course, this size will depend on the species, on the chemistry that you have in your atmosphere. And we use this spectra to try to understand what the atmospheres are made of, which is very cool because we cannot even see the planets, right? So we are studying the composition of atmospheres of planets that we cannot even see. So it's a very, very powerful technique. Just to show you why this is a great moment to do this, here is a nice movie that Hannah Wakeford made when we had the very first data of JWST coming out. And one of the planets that we observed, actually the planet that we first observed with JWST is this one, WASP-39b. We actually picked this planet. It's a Saturn mass planet. It's not too cold. It's not too hot. So it was a good planet to take as an example and to observe with JWST. And this is the transit spectrum, what I'm showing at different wavelengths. And the 2 points that you see here are the 2 Spitzer points that we had before JWST, because we've been using this technique before with the Spitzer and with Hubble. Now, you will see which is the spectrum that we got with the JWST after only one transit, so only observing the planets a few hours, and this was the data that we got. So the error bars are tiny, tiny compared to what we had before. So this is really changing and revolutionizing the field of studying the atmospheres of exoplanets, as you can imagine with this example. We have more data on that planet. So actually WASP-39b is one of the planets that I would say we know the best, because we have been observing it with all the instruments on James Webb. And here you see some of the examples with different instruments and at different wavelengths. And we detected water in this planet. We detected CO2. We detected SO2, which is this bump that you can see here. And this was one of the big surprises because it was the first time that we detected sulfur on an exoplanet. And all this is also giving us great measurements on which is the amount of metals that we have in the atmospheres. And this is really what I care about if I'm studying the interiors of the planets, because the atmospheres are really my boundary condition. So the better I know the atmospheres of these planets, this will also help me to understand the interiors as well. So together with the information on the solar system planets, together with planet formation models and atmospheres of exoplanets, all of this is really pushing me to try to understand more about these interiors of exoplanets, right? So this is really what I'm trying to do at the moment. I'm trying to put all this information together and in order to learn more about the interiors of exoplanets. Now, how is that these models of thinking now on exoplanet interiors, how is that they look like? And here you see the most common approximation that we all use when we are modeling interiors of exoplanets. That is basically saying that these planets have a compact core made of 100% metals and an envelope made of hydrogen, helium, and metals. So this was kind of like the same assumption that we were doing with Jupiter before the Juno and Cassini missions, that basically there was a sharp contrast between the core and the envelope of the planet. One thing of these models is that because this envelope is convective and fully mixed, then what we observe in your atmosphere is already giving you information on the envelope, right? So the metallicities that we observe here are telling you directly which is the metallicity that you expect in this region. And that's also why it was making our life easier when we were trying to find connections, for example, between atmospheric measurements and planet formation models, or just to say one of the things. Because we were saying, oh, I am observing this metallicity in the atmosphere. This is telling me that the planet was born in a place where there was that amount of water, for example, which is a relatively good approximation if the planets are indeed like this. Now, if we think more on what we are learning from the solar system and from planet formation models, it could actually be that the planets look more like this, where we do have a compact core, we have an envelope of hydrogen, helium, and metals, but we also have this region where the core is mixing with the envelope. And then if this is not the case, this will mean a little bit of bad news when trying to link, of course, atmospheric compositions with planet formation models. So this is, I think, something that we need to work more into the future. So thinking on those kind of models is what I was working with two of my students, with Sanne and Esther. And we try to change my Jupiter models into exoplanets to see if we could learn something about them. And then what we used as observational constraints were the mass of the planet, the radius, the atmosphere, and some assumption about the helium abundance. We then had an interior model that is similar models that we use to model the interiors of stars. The main difference is that giant planets don't have nuclear reactions in their interiors. They get their energy because they are gravitationally contracting. But basically, the models are the same. And then we use an MCMC approach, and the information that we wanted to get out of this was the amount of metals in each one of the layers and the core mass as well. So let me show you some of the results that we are obtaining. But the first thing that we did was to actually test this model with a test planet. We created a planet that we knew exactly which was the mass in each one of the layers because we invented the planet. We put error bars on the atmosphere and tried to see if we could retrieve those, the core mass that we knew the planet had. So our created planet had a core mass. So this is a core mass fraction. And the dashed line here is the core mass. So it was a tiny core, actually. We distributed more the material in the envelope of the planet. And we saw, okay, can we actually retrieve that core mass if we use only the mass and the radius of the planet? And the answer clearly, as you can see here, is no. So only the mass and the radius is very, very little to actually break all the degeneracies that we have in the interior. And it's not possible to use only this to know which is the core mass of the planet. And that is also why our models were so simple so far, because basically we just didn't have any better data to care. So even if we knew that the planets might not be like that, there was no way that we could tell with the data that we had before. But now we have better data. So then we said, like, why if we also add the atmospheric information of this planet? And you see that when we added an atmospheric model and metallicities in the atmosphere and helium abundances, then we could constrain very well with both models, which is the core mass that the planet has. So with these results, we were encouraged and we were like, okay, let's then try this with other planets. But I think that one of the important messages here is that JWST, that is measuring actually atmospheric parameters, is also helping us to understand the interiors of the planets, which I think is really encouraging for this field. So we went and tried to use our model with one example. And for that, we use WASP-39b because it's a planet that we know very well. And we wanted to see what we can say about this planet with the data that we have. So I think I mentioned this already. It's a Saturn mass planet. It's around 1000 Kelvin, around a G star. And this is the combined, it will come now. Okay. This is the combined spectrum that we obtain when we put all the different instruments of JWST together. And you see that this is just beautiful data. I mean, if you worked with exoplanet atmospheres before, this is just nothing compared to what we had before. So we really are starting to know this planet very well. And we use the derivations that we obtain with this spectrum for the metallicity of the planet to try to derive the core mass. And what we found is that here is, we are showing here the core mass fraction that we derived and the bulk metal fraction. And you can see in the red when we don't use the metallicity in the atmospheres, and in black when we use the metallicities in the atmosphere. And you see that it definitely helps to constrain the interior of the planet much better. What we are finding is that WASP-39b might have a core mass of 9 Earth masses, which is also consistent with what we are seeing for Saturn. So, which Saturn is a little bit more massive than this one, but it's encouraging. At least we are not getting a crazy number. So actually we are quite happy with the result. Now, of course, the idea is to move forward and to try to find core masses and metallicities in the different parts of the planets, try to find correlations and study the population of exoplanets. So that is what one of my students, Esther, will be doing for her PhD. And here you can see a sneak peek. So we haven't published this yet. But here is for 40 exoplanets, we did this study using all the parameters that I showed before. And in some of them, so these ones, the red and purple, we also use love numbers to constrain them even more. We have Jupiter and Saturn here as well. And the two gray colors show the results for the homogeneous and the inhomogeneous models. So you see that actually the two gray points are not so separated from each other when we are studying the total mass of metals in the planets. So if what you want to obtain, that would be an encouraging message. If what you want to obtain is the bulk metallicity of the planet, then you don't need to go to a very complex model with a compositional gradients. I think you are fine with a very simple homogeneous approximation. Now, if you want to actually understand the distribution of the metals in the interior, then that's a different story. So here I'm showing the metal, the mass metal in the envelope and the M core, the core mass for all these planets. You cannot see it very well, but actually there are large differences, especially in the core masses for these different, for the homogeneous versus the inhomogeneous model. And here is an example just to show you how the mass is distributed in the case of these inhomogeneous structures. So here you see this is the amount of metals, Z, and this is the mass. So 0, we will have the center of the planet, and here is the atmosphere. And you see that where the core is, we have 100% metal, so Z equal to 1. We have that this intermediate region is really where the dilute core is, and the metals start to dilute with the hydrogen and helium envelope. And then in the outer parts, we have the envelope of the planet where the metallicity is the same as in the atmosphere. So this is more or less how our models look like these days for these planets. All right, now just some take-home messages of this part before I move and I show you a little bit about the atmospheres. So exoplanet interiors, atmospheric metallicities, and James Webb help us to retrieve the interiors of these planets, which is really good news. We also tried inhomogeneous models, and they lead to a different distribution of metals in the interiors of exoplanets. Of course, this is something that we are trying based on solar system and planet formation models, but we don't actually know, right, if exoplanets are exactly the same as Jupiter and Saturn. So this is an assumption that I would like to test in the future. Finally, we are also finding core masses. They are not equal for both. They are not equal for all planets. This is also something that a lot of people, myself included, we were assuming in the past that giant planets have a core mass of 10 Earth masses. But this is not what we are finding, actually. This is exceptionally the case for WASP-39b, but for other planets, actually, we see core masses everywhere. So this is maybe something that would help also to understand planet formation models. Okay, so I will spend the rest of the talk now talking more about the atmospheres of the planets. Are you all still with me? Yes? A few, only a few. I will say it again. Are you still with me back there? No. Yes, I see thumbs up. Okay. So let's move now to the atmospheres of these planets and try to understand the evolution of the atmospheres. But always thinking on the metals, right? The metals is really what connects all this talk and what I care about, because it's really key to understand how these planets form. And the reason why I'm particularly curious about the evolution of the metals in the atmosphere is because I'm using that to constrain my interior models. I'm using atmospheric measurements of metallicity. And if I have any hope of understanding which is the connection between the atmospheres of these planets and the planet formation, I need to know what happens with those metallicities with time, what happens when the planets evolve. And that is really why I'm interested in the evolution of the planet atmospheres. So why is that these atmospheres evolve with time? This is basically particularly for the case of exoplanets and particularly for the case of transiting exoplanets. They are very close to their stars. At least these are the planets that we can observe today. And because they are so close to their stars, there is a huge interaction between the stellar light and the atmospheres of the planets. In particular, some of the atoms and molecules that are very high up in the atmosphere receive a lot of energy from the stars that excites them, increases their kinetic energy, and some of them might escape to space. This is also happening in our own atmosphere right now, but at a very low rate. The thing is that these planets that are so close to the star are bombarded with all these very high energy radiation all the time, and the atmospheres escape very, very fast. So in a bulk motion, they escape very quickly. So this was, of course, known for a long time, and there are lots of studies on this. But in particular, what we did with one of my students, with Amy Luca, that actually will be visiting Heidelberg next week, we studied how is that combining the evolution of the planet, the interior evolution of the planet, with the atmospheric escape, how is that affecting the atmospheres of the planets. So what you can see here, it's simulations of different planets. So she calls it the Pac-Man plot. I guess you can imagine why. But this could be very well just a series of dots. So each one of these each one of these is one model. So it's one planet that is located at this distance. So let's say the inner one is at 0.01 AU. And then we have the next one at 0.02 AU and so on. So all these models are going farther away from the star. And the different colors represent the envelope fraction that the planet has left after 10 giga-years of evolution. And these planets that you see here all were giant planets, giants a little bit smaller than Saturn in this case. But you can see that the ones that are very close to the star, they lose the entire atmosphere after 10 giga-years. And the ones that are farther away, they actually keep their atmospheres. And this is, again, the effect of the interaction with the star. Now, she went ahead and did also for a huge grid. I'm just showing one part of these. And she did it for different masses. And you see that planets that are more massive, they are more prone to keeping their atmospheres because their gravity is larger and it's more difficult for the particles to escape. But if the planets are smaller, then they actually lose a huge percentage of their atmospheres during their evolution. So we went ahead with this and we studied two different extreme cases. We studied, on the one hand, our favorite planet by now was 39b. This is, as I said at the beginning, a Saturn mass planet, so it's a big, big one. And we saw which is the metal enhancement, which is how is that because the planet loses hydrogen, because hydrogen is lighter, then the other metals remain. So the idea was to see exactly what was happening with that. And you see that actually the enhancement is not very large for this planet. It's around 1.25%, so almost nothing. So, and the reason for this is because this is a very massive planet. And then it manages to keep a lot, so it's not escaping as efficiently as with a small planet. But even when it's escaping, at the beginning, the material just all of it escapes very, very quickly. And then the hydrogen escapes, but it also drags metals with it. So this is really why there is not a huge enhancement of metals. And then when this flux diminishes a little bit, and then we could have this fractionation, let's say, that only hydrogen escapes and the others stay, then this planet was just too massive to let any other material to go out. So we don't see a huge enhancement or change in the metallicity of this planet with time, which is telling us that actually the metallicities that we observe today probably were there from the formation. And this is encouraging if we want to say like, hey, look, this is actually a primordial metallicity. So we can start trying to think about learning from this planet and formation processes. Now, our second example was a super Neptune. This planet started as a 26 Earth masses, and after 10 giga years, it ended up as 13 Earth masses. So it lost half of its mass in 10 giga years. It's a lot, it's a lot. And here you are seeing the enhancement of the metals. And in this case, the enhancement was so large because basically a lot of the hydrogen escaped and some of the materials remained, that we could actually even see the fractionation of the different elements. So if you look at iron, iron is the heaviest, so then it's the most difficult for hydrogen to drag. And that's why the enhancement of iron is the highest. It's approximately 70%. And then, but we also see changes in carbon, in oxygen, in magnesium, in all these species actually change with time. And we even see changes in the carbon to oxygen ratios. So these carbon to oxygen ratios that we really like to observe in exoplanet atmospheres, well, they actually change with time for these kind of small planets. So we also have to think about that when we are observing our atmospheres. One final thing is that because the planets change with time and their metallicities in the atmosphere and the elements change with time, also the spectrum will change with time. And she modeled, which is the spectrum that she expected for this super Neptune that ended up as a sub-Neptune, actually, with time. So you see that at zero, when the planet was born, let's say, you can see all these, let me see, you have the water features here, you have this big feature of CO2. And then when the planet started to evolve with time, the hydrogen escapes. So there is, you have water here, but you also have the CO2 that got more pronounced. If you go to very late stages, you see the sulfur appearing because sulfur is one of the things that gets enhanced the most. So, so she's saying that if you are observing sulfur, your planet is either too enriched in metals or is too old, which I think is an interesting thing to contrast with observations. All right, so the final message here is that super Neptunes suffer extreme mass loss that really influence the metallicity and abundance of individual metals, which is very interesting because we are talking about fractionation and evolution of different elements in exoplanet atmospheres. Okay. So during this talk, I walk you through the metals in the interiors of the planet and what do we expect, specifically thinking on the lessons that we learned from our solar system planets. I also tell you a little bit about the work that we are doing, trying to understand how these atmospheres change with time. And of course, these things depend on the planet that you have. So it's something that we will need to do case by case and maybe try to do some statistics once we get more data in the future. I also would like to thank my collaborators because, of course, I didn't do all this work by myself. In particular, my 3 students, Sanne, Esther, and Amy, that did most of the work, and other collaborators from the early science program for transiting exoplanets that did the amazing observations of WASP-39b, and the interior working group of the Juno mission that also was very helpful trying to understand the interiors of the giants. And thank you for your attention.
So we are going to start taking questions, and we start with the students. We'll have questions from students in the room. Yes.
Hey, hi, Jimmy. Thanks for the very nice talk. I do have a question about the interior model that you were trying, that you first tried on your toy model and that you then tried on WASP-39b. My question is, have you also, or is it possible to try it on Jupiter? And did you then get results that were, well, compatible with what we measure from other measurements?
So the model was based on Jupyter model. So we started with Jupyter and then we adapted it to exoplanets. So I would expect that yes, but the thing is that we simplified it a lot to work with exoplanets. And the Jupyter has this phase transition of helium. So that means that you will have more helium in the interior than in the atmosphere. And we don't have that for exoplanets. And helium actually has a huge because if you have more helium, you can put less metals. So I expect that there will be deviations if I apply a model for exoplanets to the Jupyter case. So this is definitely one of the things that I want to explore in the future, right? If you go to colder planets, more Jupyter-like, then where is that this transition, this phase transition happens and how we can apply that. So, yeah.
More questions from the audience?
Thanks for your talk. I really appreciate it. We don't get talks about planets here too often. So I'm interested in the internal structure. It's very interesting to see that there may be this gradient in chemical composition with radius. And my impression is that this is set by relatively microscopic processes that redistribute the metals or some very small scale processes. I think you didn't talk much about mixing due to fluid motion, so convection and uncertainties related to that. Could you comment on why convection is important in the interiors of planets, maybe which of the planets, and yeah, what's the most important uncertainty?
This is what I train for.
No problem. Okay, better now. Yeah. Yes. So the thing with these compositional gradients, so you are right that the convection, the way that the planets transport energy in general is definitely important, and it's a huge unknown that we have for the giant planets. So for example, for the stars, because we have astroseismology, we can map the radiative and convective regions in the interiors. We don't have that for these ones. So we really have no idea. And for, I would say, even before, all the time before Juno, we assumed that everything was convective in the interior and well mixed. Now, with these compositional gradients, what happens is that if your gradient of metals is too steep, that might inhibit convection. And then you actually have a different way of transporting your energy in those layers. This is something that we are starting to study now, and we are actually using some models similarly to what they do for stars to try to understand how is this transport happening. But right now, the models that we have are all stable, so we don't have that problem. But if your gradient is too steep, we think that maybe that happens in Uranus and Neptune's interior. Then we need to care about other things, and we are just working on that right now. Yeah.
Do you have more questions?
Hi, Yamila. Thanks for the very nice talk. So I have a question about Amy's work. So basically, you're assuming that the atmosphere metallicity is starting with solar metallicity for both the starry. I'm curious, so how would you think this will change if you are using a higher metallicity since, well, according to recent observation, especially this cold Jupiter direct imaging more, it seems it's overall very metal enhanced, like 1 magnitude or even sometimes 2 magnitude. So this young planet seems to be very metal enhanced in the atmosphere. So yeah, maybe that's the second question. So how would you comment on this part? So why this young planet are so metal rich in the atmosphere?
Yeah, so those models that I showed that are all starting with solar composition. And she did also a big grid trying to change the initial metallicity of the planets as well. And the results change, of course, because if you don't have the same amount of hydrogen that will drag your metals, then the escape flux is different and also the fractionation is different. So it depends on the case. But in general, when you have less hydrogen, then the escape is not so efficient because the atmosphere is heavier. And then you find less escape and less fractionation as well. Now, for the young planets that have high metallicities, probably my explanation at the moment would be that they were born that way. So if you look at the Saturn has quite a high metallicity, it's 10 times solar. So it's very possible that the planets are enriched from the beginning, and they enriched even more with time, right? So we need more observations on these young planets. I think there was a large program accepted on young planets. I'm really looking forward to see what we observe with more of those to have more statistics. But it's definitely something to learn. Yeah.
More questions from the audience, maybe from the people on Zoom as well? I don't see any messages or hands up.
Thanks. So back at the beginning, you were talking a bit about how Juno was used to measure the gravitational oscillations. And my question is it really so simple as, everything is explained by Jupiter, or when you're doing this, do you also have to account for moons and, other planets, all of these things? How complicated is this?
Yes, very complicated. So of course I made it simple. No, you have so there was the way that the interior working group worked is that we were divided mostly in 4 teams. There were 2 teams that were independently analyzing the gravity data and giving it to us. And there were other teams, mine and others, that were doing interiors. And then we were only publishing something when we all agreed. So we had huge discussions about all of this. And regarding the data, I was not doing it myself, but they were correcting for starting from the Galilean moons, the other satellites, the plasma torus around Jupiter, even the weather, because basically we had a huge antennas, radio antennas here on Earth that were communicating with the spacecraft. There was one in New Mexico, another one in Argentina, and they were even correcting about the weather of those so yes, very, very complex. It was not as simple as I showed it at all.
Also, another question about Jupiter. You were talking about the hydrogen helium transition inside this ring, and you were saying, okay, we observed this somehow, but could you elaborate a little bit more how you came, from which data you came to the conclusion that this exists? Thanks.
Yeah, so we had Jupiter is one of the planets in the solar system that we know the best because we had something like, I think, probably around 10 missions that went to Jupiter. We had the 2 Voyagers, the Pioneers, even the ones going to the outer planets, they do orbits around Jupiter to get gravity assistance. So we got, New Horizons, Cassini. But one of the most important ones was the Galileo mission that went there in the 90s. And the Galileo mission had a probe that entered into the atmosphere and made in situ measurements. So thanks to that is that we know the abundance of helium, of neon, of all the noble gases that you wouldn't get in any other way. And there we measure the depletion of helium compared to the sun, compared to the protosun. And because, they were born from the same disk, helium is a noble gas, it doesn't interact with anything. You wouldn't expect it to be different. So the fact that it's depleted, and we also observed that in Saturn, it was further evidence that there was something that was capturing helium and dropping it in the interior of the planet. And there were a few theories before that measurement, very old papers from the 70s, that were already saying that this helium rain might happen. And of course, when we got those measurements in the 90s, they just put all of it together. So that was, I think, the most strong evidence that we were using so far. The paper that was published recently, only a few years ago, they are lab measurements. I'm not completely sure of how is that they do those lab measurements because you need to reach very specific pressures and temperatures. But they did experiments of high pressures at certain points, and they got that immiscibility transition. But it's only one paper, so I really would like to know more. We also have simulations, by the way, quantum simulations and ab initio calculations of that as well.
More questions from the in-person audience or the Zoom audience? No? Okay, I think we can wrap it up then. So before the final round of applause for Yamila, I have 2 announcements. Yes. Number 1 is that next HJAC will be by Flor Garden next week on Tuesday, 16:30. She will be talking about gravitational wave paleontology, a new frontier to study massive stars across cosmic time. Tuesday, 16:30, gravitational waves, be there. The second announcement is we are having drinks right after the talk with Yamila at 17:40 in Bayrou. Yes. If you're interested in joining, this is particularly targeted at students. It's a safe space to ask questions to Yamila about her science and also a unique opportunity for networking. So if you're interested to join from here, follow Angelique, please, right there. And after that, at 7 o'clock, we are meeting for dinner at Schulze Pizzeria. Thank you so much, Yamila. Round of applause for her.